Okay, so I've started the recording. So welcome to the first training session for the Chemistry Olympiad 2025. All right, so this training session will aim to cover some of the concepts that are typically covered at A level. All right, so things that you may not learn at secondary school, because some of this knowledge could very well be useful for you to answer the questions in Chemistry Olympiad later on. Now, every notes will start off with recap. So over here, I'm actually recapping what are the subatomic particles in an atom, the three subatomic particles, protons, neutrons, and electrons, which of course differ in terms of the charge, mass, and the location within the atom. All right, so this one I trust, okay, we can read it and we will get the recap. Let's move on to page 2. The behavior of these three particles under the influence of an electric field. Now, the meaning of the word electric field is basically a region of space where an electrical charge will feel a force. So, for instance, I can have an electric field if I have negative and positive plates facing each other. These are plates. One plate is negatively charged, the other plate is positively charged. And now we need to think of the behavior of some of these subatomic particles. For instance, proton. Protons are positively charged, so naturally they are attracted to the negative plate. On the other hand, electrons are negatively charged and therefore they are deflected or attracted towards the positive plate. You notice that neutrons are undeflected. They do not bend, they do not curve towards any plate, and that makes sense because they don't have charge. Okay? Now, the second thing we realize is that the protons and electrons, they curve to different extents. They are deflected to different extents. And this is because the deflection, the curvature of the pathway is proportional to charge over mass, or what we call the charge to mass ratio. All right? So, higher charge, higher deflection. Because charge is in the numerator, so higher the charge in terms of the number, if it's 2 minus, it has a higher charge than 1 minus, for example. So higher charge, higher deflection. On the other hand, if the mass is higher, it's heavier, the deflection will be lower. This is because the mass appears in the denominator. So if the mass is bigger, then the denominator is bigger and therefore the deflection will become smaller. Okay, so as you can see, the electrons are curved more. They are curved and deflected more drastically than protons. And that makes sense because electrons have a smaller mass, more deflection. Okay, so electrons are deflected more than protons as it has a smaller mass. And this brings us to question 1. Now that we have considered protons and electrons, let's consider two different ions. So in 1A, for example, you have Li plus and Na plus. If you just look at the charge, plus, plus, they are both the same charge, 1 plus. All right, so charge clearly is the same in 1A. However, the difference lies in the mass. So where do you actually get the mass of these ions? You can get the mass of these ions by referring to the periodic table. So if you don't have a periodic table handy with you now, please get a periodic table. You can find one in your textbook. You could find one in the 10-year series. You could also find one online. If you look at the mass of Li plus versus Na plus, you will realize it's quite different. Lithium has a mass of 7, whereas sodium has a mass of 23. So immediately you can see that lithium is much smaller in mass. All right. Now you think back towards deflection. Deflection is proportional to charge over mass. Lithium, having a smaller mass, should be deflected more. All right. So that's 1A. Now we move to 1B. If you look at 1B, we have F minus versus O2 minus. So immediately, I think you can easily work out as well. The one that will be deflected more should be the one that is higher in charge as well as smaller in mass. On both counts, The O2 minus ion has higher charge because it's doubly negative. Remember, we are looking at the number, the magnitude of the charge is 2 minus. 2 minus is a higher charge than 1 minus. So this has higher charge than F minus. In addition, it has a slightly smaller mass than F minus as well. If you look at the periodic table and you compare the masses of oxygen versus fluorine. All right. So now I shall leave 1C for you to think about. Okay. 1C, which of the two ions will be deflected more? Okay, let me just give you a few seconds to think about 1C. And then thereafter, can you please type your answer, which particle will be deflected more, into the chat? Okay, so usually we will give you questions whereby it's quite straightforward. Okay, it's quite clear one ion will be deflected more than the other. Okay, so of course, Leon, you're asking which ion will deflect more if one ion has higher charge, but the other one has lower mass. That is a more ambiguous situation. So usually we will have to do the experiment to find out. All right, so I can see some of you responding for 1C. Yes, indeed, for 1C, Mg2 plus will be deflected more. Okay, higher charge, smaller mass as well. All right, magnesium has a much smaller mass than potassium. All right, so that covers the deflection or behavior of charged particles in an electric field. Okay, so this is what you commonly see in the first chapter of A-level H2 Chem. All right, now moving on. If you look at the next page, it's also recap, but this one, let's just go through it. I'm sure you will realize that this is an element called iron. Iron is found in the periodic table. And in the periodic table, you can look for the chemical symbol, the name, as well as you get two numbers, the proton number and the mass number. Now, importantly, you need to know proton number is also called atomic number. So proton number and atomic number, they are the same. Mass number would also be called nucleon number. Now, this word nucleon refers to whatever is in the nucleus. In the nucleus of an atom, you have protons and neutrons. Okay, so the mass on the nucleon number is a sum of the protons and neutrons in the nucleus. So for iron, we can quickly work out it has 26 protons because the proton number is 26. For an atom of iron, because for atoms, they have not lost electrons yet, the number of electrons should be equal to the number of protons. So iron atom also has 26 electrons. And finally, in terms of neutrons, it'll be 30 because we take 56, the mass number 56 minus 26. All right. Now, this one is a recap. I'm sure you remember this. Our goal now is to focus on the electrons for the next 30 minutes. We are going to look at how to write electronic configuration of elements different from what you have learned in Sec 3. All right. We are now going to use a more advanced version of how to write the electronic configuration so that you can write the electronic configuration of every single element, not just the first 20. So if you recall in Sec 3, we told you that electrons are located in electron shells. And we have taught you that the first shell holds a maximum of 2, the second shell holds a maximum of 8, the third shell holds a maximum of 8. But with these rules, you can only write for the first 20 elements. So now the question we have to ask ourselves is, why is it that the third shell will only fill 8 electrons, given that the third shell is further away from the nucleus and probably bigger? All right. So this is an important question for us to ask. Why on earth would the third shell only accommodate 8 electrons? It should accommodate more, given that it's bigger. And the answer to this is, we need to understand each electron shell can be further subdivided. Each shell can be further divided into subshells. All right. And now I'm going to bring you through the subshells for every single shell. So please stay with me on the next table. The next table is very crucial. All right. So we start with the simplest, the first shell. Remember, the first shell is the closest to the nucleus. Okay, closest to nucleus. All right. So the first shell must be the one that is filled first. All right. Now, the first shell only has one subshell. First shell contains the subshell called 1s. All right, 1s. Now, the 1s subshell only holds 2 electrons. And that's why the first shell only holds 2 electrons in total, because the first shell only has one subshell. Then we move to the second shell. The second shell has 2 different subshells, the 2s and the 2p. All right, 2s holds 2 electrons. 2p, however, can hold 6. So what do you notice? The second shell in total can hold 2 plus 6, 8. And that's why you have learned the second shell holds 8 electrons, because the second shell has the 2s subshell and the 2p subshell. 2s holds 2, 2p holds 6. Now, at this juncture, you must be wondering, what does the 2s, the 2 mean? Does it mean 2 times s, like in algebra? The answer, no. All right? The numbers in front of the subshells do not mean we multiply. We do not multiply. The number in front tells you which shell is it from. So 1s just means it's the s subshell from the first shell. 2s means the s subshell from the second shell. Similarly, 2p means the p subshell from the second shell. All right? And now I'm sure you can figure out a pattern. If it's s subshell, 1s, it will hold 2 electrons. 2s, also 2 electrons. So we can generalize and say s will always be 2 electrons. P will be 6 electrons. The next one is D. All right. So now if we go to the third shell, the third shell has a 3s, 3p, 3d. The third shell has 3 subshells. That makes sense. First shell, 1 subshell. Second shell, 2 subshells. Third shell, 3 subshells. All right. 3s holds 2 electrons. 3p holds 6 electrons. Let's look at 3d. 3d holds 10 electrons. You can clearly see a number pattern here, right? From S to P to D, you can already see, right? I am increasing by 4 electrons each time. So the S holds 2 electrons, the P holds 6, the D holds 10. So I'm sure you can predict the next one is called F. The F subshell can hold 14 electrons. All right? And that's why this is called the SPDF notation for writing electronic configuration. The S, P, D, and F refers to the subshells. Okay? First shell only has 1s. Second shell will have 2s, 2p. Third shell, 3s, 3p, 3d. All right? Fourth shell, 4s, 4p, 4d, 4f. All right? So now if we look at the third shell has 3s, 3p, 3d, 2, 6, 10. So in total, 2 plus 6 plus 10 equals 18. So in reality, the third shell can accommodate a maximum of 18 electrons. All right? So why then do we teach you in Sec 3 that for the third shell, we only feel 8 electrons? And that is because of the next page. Now, the idea is the electrons must go into the shells and hence the subshells in a certain order. The order you have learned so far is in terms of shells, first shell, second shell, third shell. But now you have learned subshells. So let's learn the order of filling up the subshells. Now, there's a diagram here that looks pretty complicated, but the idea is we will start from the lowest. 1s must be filled first. Then you go on to 2s. Then 2p. Then 3s. Then 3p. But this is where the problem starts. After 3p, we do not go to 3d. We will go to 4s first. So this is the most important. You need to highlight this. After filling up the 3p subshell, we shall go to 4s subshell first. That means we ignore the 3d subshell for the time being. All right. So now I'm going to do a short example of how this works. All of you know this element. This is the symbol. Ca is a symbol for the element calcium. If you look in the periodic table, which I hope all of you have by now, and I hope all of you already know this, calcium has 20 electrons, right? So how do you fill up 20 electrons? Well, let's think. We start with the 1s. 1s can hold how many electrons? So if you look back at the table, 1s holds 2 electrons. So look at how I've written it. 1s2. The 2 is written on top. So what this means is that there are 2 electrons in the 1s subshell. Okay? So the 2 is written as a superscript on top. 1s2. So 2 electrons goes into the 1s subshell. That makes sense. After 1s, we go on to 2s. How many electrons can a 2s subshell hold? The answer is 2. So 2s2. S always holds maximum 2 electrons. All right? So we have 1s2, 2s2. After 2s is filled, we go to the next one, 2p. P can hold 6. Therefore, 2p6. So at this stage, you must start counting. I have filled 2 electrons, 2 electrons, 6 electrons. So 2 plus 2 plus 6 is 10. 10 electrons already. We are not done yet because we have 20 electrons, so we must continue. So after 2p, we go to 3s. All right. How many electrons can go into 3s? Again, it's an s subshell. Even though it's 3s, it's still an s subshell in the third shell, right? S only holds 2. Then we go to p. 3p. P holds 6. At this juncture, you better start counting again. How many electrons already? 2, 2, 6, 2, 6. So add all together is 18. All right. So far we have filled 18. But I have 20 electrons. So I should have 2 more going somewhere. Where is that somewhere? So this is very important. You need to realize after 3p is not 3d. We will go to 4s first. And now let's think. 4s can hold how many electrons? Again, it's s. S subshells hold 2. So 4s2. And that makes 20. So now you have learned the A-level version, okay, of how to write the electronic configuration in the SPDF format. But let's link this to the Sec 3 version. You have learned in Sec 3 how to write the electronic configuration for calcium. First shell, 2. Second shell, 8. Then the third shell, we have 3s, 3p, right? The third shell over here, 8. And finally, the fourth shell, 2. That's why in Sec 3, we taught you 2, 8, 8, 2. All right? The reason why this works in Sec 3 is because we stopped at calcium. All right? We didn't go on to the subshells. All right? Now, this is how we write the electronic configuration at O level 2882. And at A level, you will write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, what if the final subshell is not completely filled? For example, if you only had 19 electrons, potassium, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. That's why it's 2, 8, 8, 1. All right. Now, we are learning the SPDF format not just to deal with the first 20 elements. Now we're going to practice how to write the electronic configuration for elements beyond, all right, the first 20. Okay, so why is the 4s subshell filled first? Now the 4s subshell is filled first because the 4s happens to be closer to the nucleus than 3d. All right, the s subshells tend to be closer to the nucleus. So at the third and fourth shell, the 4s starts getting closer to the 3d. All right, so this is a pattern and order that you will have to learn. So now let's move on to iron. Okay, Mr. So has already given you the answer there, but let's do this together. Okay, iron. Iron, we figured out just now, has 26 electrons. So how to write? First, we start with 1s, 1s2, all right? Then 2s2, 2p6, 3s2, 3p6. So up to this stage, very safe one. You can continue because this is 18 electrons so far only, but you have 26, right? So you got to move on. So after 3p, what's next? You got to remember, after 3p, the next one is always 4s. Do you notice I leave a space between the 3p and the 4s? I left the space deliberately because I know 4s only holds 2 electrons. Therefore, I've only filled 20 electrons. I still have 6 more. And the 6 more needs to go into the 3d. We will still write the 3d. Oh, sorry. We will still write the 3d between the 3p and the 4s as a convention, as a habit. But do know that the 3d is actually filled after the 4s. Okay, so this is how we write the electronic configuration for an iron atom. 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. All right. Now, there are some questions about what do the subshells visually look like. That is actually on the next page. So we will deal with what the subshells look like on the next page. All right. But in the meantime, this is time for you to practice. Now, I cannot see you practicing, of course, because you're online, but it's time to try writing yourself for 2A to 2F. Now, I'm going to give you some time to work on this. Can we just take about 6 minutes, all right, to work on writing the electronic configuration for writing sodium atom, chlorine atom, sodium ion, chloride ion, titanium atom, and bromine atom. So let's do it now, all right? Let's do all 6 before I give you the answers, okay? Yes, 4S is filled before 3D, but when writing the final answer, we will still, out of habit, write the 3D before 4S in terms of presenting our answer. So yes, even though the 3D is filled after 4S, we will still write it such that it appears to the left of 4S, okay? It's just a matter of writing, but in reality, it's filled after the 4S is. That's why you must remember to leave a space. If the 3D is filled, you have to leave a space to put the 3D there. Write like reality cannot, okay? Because at A level, that's how they will write. Okay, they want neatness. It's neater to see the 1, the 2s, the 3s, the 4s together. All right, that's how we will do it. Okay, if you go online and search also, okay, they will always give you the electronic configuration in this manner. It's a habit. All right, but those are good questions. Okay, so I hope we are already on 2B, chlorine atom. Okay, so I'll also start writing the answers for you so you can check your answers as you do them. Okay, you must do all 6. Maybe let me use a different colored ink so it's neater. Okay, so write the electronic configuration this time around in the SPDF format. So you can check whether you're on the right track. 2A, sodium atom should look like this. 1s2, 2s2, 2p6, 3s1. All right, which nicely maps to the 2, 8, 1. Right, first shell 2, second shell 8, third shell 1. So there's a sodium atom. Now let's do the chlorine atom. Okay, check whether your answers are correct. Okay, so 1s2, 2s2, 2p6, 3s2, 3p5, which nicely maps to first shell 2, second shell 8, third shell 7, 287 for chlorine, right? Okay, let me give you a while longer to work on the 2 ions before going to titanium. Once you have gotten the atoms correct for sodium and chlorine, you should be able to work out the ions quite quickly if you remember how the ions are formed from the atoms. Okay, so the sodium ion, if you recall, sodium is in group 1. Group 1 elements have 1 valence electron. That makes sense, right? 3s1, right? 1 electron in the outer third shell, all right? So sodium is not stable. It's reactive. So what will sodium do? Sodium will lose the 1 valence electron. It will lose the 1 electron in the 3s. Therefore, the ion formed at the end by sodium has lost the 3s, meaning it's simply left with 1s2, 2s2, 2p6, because that 1 electron in the 3s is lost. Okay, has been lost. All right. So the sodium ion is just 1s2, 2s2, 2p6. Now moving on to the chloride ion. The chloride ion comes from chlorine. Okay, if you recall, chlorine is in group 17. It has 7 valence electrons, so it will gain 1 more in order to achieve a fully filled outermost shell. So it's quite clear, again, it has to gain 1 electron this time. So you don't get rid of any electrons. Instead, you gain more electrons. How many more? Just 1 more. And that fits nicely into 3p. Therefore, it's now 3p6 for the chloride ion. Right? So 1s2, 2s2, 2p6, 3s2, 3p6 for the chloride ion. Okay, so that's it for the 2 ions. Now let's move beyond. We will move beyond the 20 elements. Now we are in the realm of the 20 plus electrons or the 30 plus electrons. So titanium, if you look at the periodic table, which I am actually going to look because I don't exactly remember, titanium has 22 electrons, right? I hope you have found titanium. Titanium has 22 electrons. So clearly, it has gone beyond the usual O-level elements, the usual rules. So we are going to need the SPDF format to answer this. So 22 electrons, how do you write it? 1s2, 2s2, 2p6, 3s2, 3p6. Up to this stage, very safe because I know that this is only 18 electrons. Okay, up to this stage is 18 only. I got 22 electrons, so I got 4 more that I need to fill in. So how do you fill it in? Remember, after 3p is 4s. S holds 2, so 4s2. But I leave a space. I deliberately leave a space because I know I'm going to need the 3D subshell now. And by convention, even though the 3D comes last to fill in, but I need to leave a space to write it in. All right, so leave a space. So now if you do the addition up correctly, you will need 2 electrons in the 3D. All right. So ensure that you add up all the electrons to make sure you get 22. All right. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2. All right. Now for the Sec4s, I'm sure you have learned titanium is an example of a transition metal. Transition metals are famous because transition metals can form ions with variable charges or variable oxidation states. Okay, so I shall leave you all the thing. Titanium has Ti2+. Titanium also has Ti4+. These are the two most common ions that titanium forms. Why doesn't titanium form Ti1+ or Ti3+? You should be able to explain it using this. All right, so I'll leave you to think, why is it titanium only has Ti2+ and Ti4+? All right. So now let's move on to the last one, bromine. So you also need to look for bromine in the periodic table. So bromine is Br. So look for Br in the periodic table. Look at how many electrons it has. Okay, so if you found Br, it has 35 electrons. So again, it's way beyond 20, right? If it's beyond 20 electrons, you're going to need this SPDF format. So how do you do 35? Again, we start with 1s, 2, 2s, 2, 2p, 6. So by now, you should get a hang. S is always 2. P is always maximum of 6. All right, so 1s2, 2s2, 2p6. Then we go to 3s2, 3p6. Okay, so I'll always write this first because I know this is 18 electrons. All right. So we have filled 18 already, but bromine has 35 electrons. Therefore, we are going to need to move on. So after 3p, remember, you need to move on to 4s. But leave a space, please. 4s, s holds 2. So far 20 electrons. Then now we go back to 3d. Right? We have to go back to 3d. 3d holds how many electrons? Remember, s is 2, p is 6. It's always a +4 addition, right? D maximum 10. So S is 2, P is 6, D is 10. So if you add up properly, thus far, you have filled up a total of 30 electrons. Right? But bromine has 35. So what next after 3D? It must be 4. Because the third shell got no more subshell. The third shell only has S, P, D. Right? It must be the fourth shell now. So the fourth shell, but S is already done. What's after S? P. So 4p, 5. And that's how you get 35. Okay? So bromine is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p5. All right? Now, of course, this looks very complicated. If we were to rewrite bromine in our O-level format by shell, how do I do that? I can do that, no? The first shell, 2. Second shell, A, right? Third shell, 3s is third shell, 3p is third shell, 3d is also third shell. So the third shell maximum, you look at it, 2, 6, 10, 18. So the third shell holds a maximum of 18. And finally, the fourth shell, 2 plus 5, 7. And that makes sense. Bromine has 7 valence electron. Hence, bromine is group 70, just like chlorine is. All right? So now, if you look at it, okay, you have figured out how come bromine is also in group 17. Okay, it doesn't contradict what you have learned in Sec 3, Sec 4. Because in Sec 3, Sec 4, we look at valence electrons based on the shell. The valence shell is fourth shell. There is a total of 2 plus 5 equals 7. 7 valence electrons. Therefore, bromine is indeed from group 17. And bromine will gain 1 valence electron, just like chlorine will. Okay? Now, I hope this has opened up more perspectives for you. All right? So this is an important exercise. So now, okay, through the Chemistry Olympiad, I also hope that you all learn more content. But at the same time, it also links back to what you learned in Sec 3 and 4. So that you know that we are not deliberately lying to you, but it's just that the model of the atom has become more sophisticated in upper levels. All right. Now, so there are a lot. So can we write the SPDF in O level? The answer is no, you can't. All right, you can't, because at O level they are expecting the simpler version. Now you're wondering how come we don't just teach the more complicated version at one go? Why don't just teach the more complicated SPDF version in Sec 3? The answer is on the next page. All right. Now let's move to the next page. If you are done copying, okay, you can also give reactions. I've realized. You see the smiley, send a reaction, right? I guess you can send a reaction, okay? If you're done. Okay, great. All right. Now, the reason why we cannot write this way at O level and we cannot teach you this way at O level is because what do the subshells actually look like? The answer is actually the subshells themselves are further divided up into things called orbitals. All right. So the subshells themselves are divided into orbitals. So you can divide it even further. And orbitals are where the electrons are located exactly. And the irony is, electrons actually, the location, you cannot define it with 100% accuracy. Scientists can only say electrons are most likely to be located here in this region. It's a probability of being here. All right. So the region in which electrons are most likely located is called orbitals. And to teach you SPDF means we need to teach you the shapes of the orbitals. What do they look like, right? Many of you ask this. And this is what they look like. And you notice immediately, you have the x-axis, the y-axis, and the z-axis. And this is why you need math. All right? The shapes of these orbitals, and hence the subshells, are obtained by solving equations. Every single one of these shapes can be described using the coordinates x, y, and z. So it's an equation in x, y, z which describes the shape of these things. So for the Sec 4s, you have already done A math. You would have done equation of a circle, right? Equation of a circle is x squared plus y squared equals to r squared. Okay, that's the equation of a circle. But circle is two-dimensional, no? Your s orbital is called s, by the way, because it's spherical. For a sphere, which is a three-dimensional circle, if you like, you will need a more complicated equation. All right? Now, don't worry, at A level, we also don't solve these equations. To solve these equations, you're going to need much more mathematics, like university level mathematics. So when I did this in university, we will need much more mathematics to get there. I'm sure you can see the p orbitals look funny, right? They look like this weird figure of 8. It looks like 8, right? We call it a dumbbell shaped. All right, and p orbitals, there are actually 3 of them. There's px, py, pz. These are aligned along the different axes. And the equation for this is quite difficult. Okay, you will need more mathematics. Specifically, you will need polar coordinates to understand this. All right, so at A level, we also don't solve the equation. All right. Now, d orbitals is even more complicated because you can see you have like, whoa, dz squared, dx squared minus y squared. Oh, that's why algebra is important. All right. Now, don't worry, I'm not going to show you the equation, but if you are interested in the equation, all right, and the solutions to the equation, please go and Google this. Okay. It's called Schrodinger's equation. Okay. On social media, you always hear people talking about Schrodinger's cat, but actually Schrodinger is more famous for the equation. It's the equation, and after solving the equation, you will get the shapes of these orbitals. So you can Google Schrodinger's equation if you're more interested in how these orbitals and subshells look like. All right. Okay, moving on. Okay, we are doing good on time. We have about 17 minutes left. Now, I think the idea is you have finished atoms, you know atoms, how to write the electronic configuration, but that's not very interesting. We want to make good predictions about what atoms will do. In particular, you have learned in Sec 3 atoms either lose or gain valence electrons, and the purpose is to achieve a fully filled outermost electron shell. That will never change. Even when you go to university, that doesn't change. All right. But now let's put some comparisons in. Which elements will lose valence electrons more easily? So we can start to compare, right? Maybe sodium will actually lose electron more easily than chlorine. And that makes sense. So the ease of losing valence electron, how easy is it to lose the electron, is expressed by the first ionization energy of the element. All right. Now, this one you might have seen in the database questions. My Sec 3s, you confirm have seen this before. All right. Now, the first ionization energy, simply put, is the amount of energy that you need required to remove 1 mole of electrons. Mole is a counting unit, 1 electron, from 1 mole of gaseous atoms to form 1 mole of positive ions. It's easier to visualize this in the equation. Sodium becomes Na+. All right, you remove the first electron from sodium. How much energy do you need? That's called the first ionization energy. All right, so how does the first ionization energy change? Okay, so as you go down the group, does it become easier to lose the electron? So you have to think, what is keeping the electron in an atom? What is keeping it there? The idea is the valence electron is attracted by the proton in the nucleus, right? Without the protons in the nucleus to attract the electrons will just fly away. And that makes sense. So the idea is, as we go down the group, we could ask ourselves, are the valence electrons going to be more strongly attracted or less strongly attracted? One way to see this is as we go down the group 1, for example, lithium, sodium, potassium. As you go down the group, you notice that you get more and more shells. The number of electron shells increases. As a result of this, as you go down the group, the valence electron is further away from the nucleus. More shells, right? As a result of having more shells, the valence electron is further away and therefore less strongly attracted to the protons. Therefore, they will be more easily lost. More easily lost, a synonym for this is that it requires less energy to lose. You don't need to pump in so much energy input for the electron to be removed. Okay, so that's why the first ionization energy decreases down the group. It also explains to you why group 1 becomes more and more reactive, more and more explosive, violent as you go down the group. Simply because the valence electrons become more easily lost. They require less energy to be lost. Okay? Now, to understand this, you don't need the orbitals, right? So don't worry too much about the orbitals for now. I think what's more important at this stage is to understand subshells and also to understand the trend as you go down the group. Okay? The orbitals, to be really honest, even A-level students, they don't solve the equation. So they just have to learn the shapes at A-levels, but they don't have to solve the equation. You will only solve the equation to get the shapes of the orbitals if you major in chemical physics, which I did, all right, in the final year of university, right? Because you need to have done a number of years of mathematics before you get there, all right? So don't worry too much about the equations. Worry just about the idea of the subshells and the idea of ionization energy now, okay? Now that's down a group. How about across a period? Now across a period, from left to right, let's say from sodium to chlorine, you notice that the number of shells doesn't change. That makes sense because we have taught you same period, same number of electron shell. For example, sodium, period 3, got 3 shells in total, right? Chlorine also period 3 has 3 shells. So across a period from left to right, the number of shells stays the same. However, as you go from sodium on the left to chlorine on the right, the number of protons now increases, meaning you have more protons, yet the same number of shells. More protons means more strongly attracting to the valence electron. Therefore, the valence electrons are harder to lose as you go from left to right, from sodium to chlorine, because they are more strongly attracted. And that's why elements on the right don't lose electrons. They tend to instead gain electrons. All right. So that makes sense. If you think about it, sodium loses electrons, whereas chlorine gains valence electrons. And the reason, chlorine has more protons than sodium. Therefore, the valence electrons are more strongly attracted to the nucleus. So chlorine finds it very difficult to gain electrons. Chlorine needs a lot more energy, all right, to actually lose the electrons, okay? So this is across a period, down a group. Now, this is useful, even for your regular chemistry lessons. A lot of the database questions will revolve around this concept of ionization energy. Okay, now, so far we have talked about first ionization energy, which is the energy needed to remove the first electron. But clearly, some elements may lose more than one electron, right? You already know this. For example, calcium. Calcium loses 2 valence electrons. So how then do you quantify, all right, quantify the amount of energy to lose the second electron, all right? So we could define the second ionization energy. Now, the second ionization energy just means, in simple terms, the energy needed to remove a second electron. That means you're going from 1 plus, you remove one more electron, 2 plus, all right? Now, you might be thinking, wow, so ridiculous. Why would sodium form Na2 plus? Well, let's look at the numbers. How much energy? If we just look, sodium, to lose the first electron, okay, not too bad. 494, not so much. To lose the first electron, sodium still can. But do you notice, from the first to the second, there is a very large increase. It increases so drastically from the first to the second, meaning the energy needed to remove the second electron is so much more. I'm sure you can see from the numbers, right? Literally 10 times more, You need 10 times more energy in order to remove the second electron from sodium. Now, why will that be the case? Well, that is the case. These are numbers that you can find online easily. There is a huge increase from the first to the second ionization energy of sodium. That tells you that the second electron is super difficult to remove compared to the first. So where is this second electron in sodium? Remember, sodium only has 1 electron in the outermost shell. If you remove the first electron, which is in the outermost shell, where is the second one gonna come from? The second one to be removed has to be from the inner shell. Inner shells, as the name suggests, they are closer to the nucleus, and hence a lot more energy is needed to remove the second electron, which therefore explains why sodium will only form Na plus. Sodium only forms Na plus because it's so much harder, so much more energy to form Na2 plus. Because the second electron is already in the inner shell. You need so much more energy in order to form it. Okay? Now, so for such questions where we give you the ionization energies one by one, the first IE, the second ionization energy, the third ionization energy, we are just telling you how much energy is required to remove the first electron, then the second one, then the third one. Okay? So if you look at the next question, it's the same concept. All right? We are giving you first and second and third and fourth. All right? The energy required to remove the first electron, the energy required to remove the second electron, and so on and so forth. We always look for the large increase. All right? We always look for the large increase. Okay? Don't go for the small differences. Go for the large increase. If you look in question 3, the data I've given you, where is the largest increase between what and what? So if you just use your calculator and look at the numbers, you can subtract the numbers from one another. You realize that the largest increase is between the second to the third, right? It's a large increase between the second and the third. Okay, this is the largest. In fact, third to the fourth is not as large as the second to the third. Okay, so large increase means what? Oh, it means that the third electron is much, much harder to remove. Why will that be the case? Why will the third electron be much harder to remove? So firstly, let's write down there's a large increase from the second ionization energy to the third ionization energy. What this means, this implies the third electron is much harder to remove. Right? So why will the third electron be much harder than the second electron to remove? The reason is because the third electron is from the inner shell. That means the third electron clearly must be from the shell that is nearer to the nucleus. All right? The third electron is from the inner shell, which is much, much closer to the nucleus. So the question now we should ask ourselves is, okay, the third electron is the one from the inner shell. So how many valence electrons does this element X have? If the third electron is the one from the inner shell, that means the first electron is from the outer shell. The second electron is still from the outer shell, meaning X has two valence electrons. The first, the second are in the outer shell. But the third electron, which is much harder to remove, is from the inner shell. So if it has two valence electrons, it must clearly be from group 2. So X is actually magnesium. Okay, I got the data. It's for magnesium. All right, magnesium is in group 2. All right, so this is how you actually work out from the ionization energies which group an element is from. You always look for the large increase. Then you got to reason it out. In this case, the large increase is from the second to the third ionization energy. That means the third electron is much, much harder to remove compared to the second one. That means the third electron must be much, much closer to the nucleus. It's in the inner shell. If the third electron is from the inner shell, that means the first electron, the second electron are still in the outer shell. So it has two electrons in the outer shell, two valence electrons, hence group 2. All right, so this is the concept of how you use successive ionization energies. Okay, don't worry, if you don't get it right away, it's fine. All right, but you need to take it down so that at least when you go back and ruminate and reflect on it, you will appreciate much more. Okay, and this is also a hint for you when you go on to A level. If you don't understand during the lecture immediately, it's normal. However, the difference is when you go back and reflect on what you have copied down, you start thinking a little bit more. Okay, these concepts, you really need to think about it. All right. Now, the fourth IE over here for element X looks very big, right? But actually, if you count the increase from here to here, it's only about 2,300 kilojoules increase. It's not a lot. All right. Now, why does the IE still continue to increase? Now, you think about it. As you remove the electrons, do you also remove the protons? The answer is no, right? I hope the answer is no. We should know by now, right? Only electrons are lost. Protons are not. So, as you remove the electrons, you have fewer and fewer electrons left, which are being attracted by the same number of protons. That means whatever electrons are left will now feel even more attracted to the proton because there are fewer and fewer electrons, okay, to share out the positive attraction from the proton. That's why the fourth IE is actually higher than the third one, okay? And you will see that pattern. The fifth IE will be higher than the fourth IE and so on. All right? Now, this question is a very typical question. So what happens is that you need to look for the large increase in the IE. So remember, IE basically is the energy required to remove the electron. So the second IE is the energy required to remove the second electron. The third IE is the energy required to remove the third electron. All right. So if there's a large increase from the second to the third, that means you need a lot more energy. It's much, much harder to remove the third electron. Why would that be the case? That's only the case if the third electron came from inside the inner shell. The first two electrons are still in the outer shell. All right. Can? So essentially, this is something that we have to practice together. All right. Now, I'm not saying that this will definitely come out, but it's a useful concept to have. All right. Okay. I'm actually going to stop here for today. Don't worry about the ionic bonding. We can take it together with the covalent bonding the next time round. All right. Anyway, the ionic bonding portion should be quite similar to the SEC3, whatever you learn in SEC3. All right. But I wanted to spend some time on subshells and ionization energy today. That's why I present it to you. All right. Now, before we go though, let me just give you, all right, another element's ionization energy to practice with. So just give me a while. Let me find the data for another element for you to practice with so that you can tell me which group this element is from. All right. If I can find it, give me a minute. Okay, I found it. Okay, I'm just going to give you another element, a random element, and you will tell me which group this element is from. Okay, so you can take down the data, and this should hopefully be something for you to think about over the next few days. Which group will this particular element, let's call it element Y, be from? All right, remember what's the strategy? We look out for where the large increase is, and based on where the large increase is, we have to reason it out. Okay, so how many valence electrons did Y actually have? Okay. And let me stop the recording here. For those in the meeting, just stay for a short while more.